All right, good afternoon, everybody. We're gonna go ahead and start off this session. So my name is, what does the slide say my name is? I'm Bill Phillips. I am a software engineer at Cash App. If you're familiar with the blog post series RX Java to coroutines concepts that's been on the Cash App code blog, I wrote all of those, so I've spent a lot of time thinking about coroutines. I'm a contributor to Molecule and to Turbine, and I'm kind of internally a bit of a trailblazer for coroutines testing processes at Cash App. So this talk is going to be me unpacking the things that I recommend internally at Cash App. Is mainly what we're going to be talking about here. I also, if any of y'all ever read the Big Nerd Ranch Guide to Android Programming, I don't write that nowadays, but I wrote the first edition and worked on the second and third editions of that. All right, so what am I going to talk about today? First, use channels or turbines to communicate to the code that you are testing. Use channels and turbines to read data from the code you're testing. We're going to talk about race conditions, both conceptual race conditions and real race conditions. I'm going to talk about why and how to police dispatchers in the code that you have under test. And we're going to talk just a little bit about structure concurrency. Now, before I get into the main meat of the talk, a warning. This talk does have non-exemplary code in it. So I'm going to have slides in here that have code that I would not recommend writing, that in a code review that I would flag, and that we are going to later in the session talk about alternatives for. That's just kind of the path we're going to be traveling here. But so that you know what it is, you will see this lovely little icon of eyeballs and a red arrow every time I have some non-exemplary code. I will not talk about it every time you see it. Sometimes we'll be just skipping past it, but we will address everything that I call out eventually in the session. And then finally, I want to talk a little about mistakes. If you do something, like this is going to be a very prescriptive talk. If you do something that I prescriptively say, oh, this is awful, that's fine. You know, like this is part of life. Everything that I recommend here, I arrived at by having it go horribly wrong and doing something otherwise. So, you know, mistakes mean that we're trying and we're growing. That's totally fine. Having got all that behind us, let's write some code. So the example we're going to use throughout this session is a little biometrics presenter. So this is going to be a very minimal presenter, but we're going to use it to just explore testing ideas in asynchronous code. We're going to use the API, one of the APIs that we use internally in Cash App for our business logic. We do unidirectional. The way we represent that is by having a flow of events and an output flow of UI models. These are just data objects that program the user interface. Our biometrics presenter, I don't want to talk about event handling, so it's just going to be a flow of unit events. We're not going to do anything with it. So we're going to start by emitting a loading event, and then we need to interact with biometrics somehow. And so for that, I'm going to use a simplified version of the API that we use and built internally in Square, which is something we call biometrics store. So we'll just read the biometrics token from our biometrics store. This is a suspended call. It'll display a user interface, ask for a fingerprint, all that kind of fun stuff. And then, of course, we need to have a key value to read, so we're going to inject that key as well. And then once we're done with that, we're going to emit a done event so that the user interface is displaying not loading indicator anymore. Finally, once we're done with that, we want to navigate to the next screen. So let's inject our navigator and then see if that token is null. That means we should go back to the home screen. If it's not null, we want to go to the main screen. So that's our presenter. Any questions about this before I move on? Awesome. So let's write a test. So I'll write biometrics presenter test and start off with run test, our modern coroutines testing tool. Inside of that, I'm going to need to have some collaborators for my biometrics store and my navigator. Now, What do I want to use for these? I could either use a mocking framework to create these, or I could write my own. That's building a fake version of that. So which one do I want to do? Well, I want to do fakes, and let me lay out my reason for this. It's because, one, I don't want to explain how mocking works. I prefer fakes. I would rather not explain myself at all at this point in the talk, to be honest. And I don't have all day here. We got to get this successful. So here are our fakes we're going to build. So these are just simple fakes built off of, like, we have a map that has our biometric stored data in it. And then inside of our fake navigator, whenever we get a call to go to, we're just going to write that to an internal var. This is pretty much exactly what these fakes looked like in Cash App a year and a half ago. They don't look like that now because this is not exemplary code. But we'll construct those and then get a key and a token, build our instance of biometrics presenter, get a flow off of that, and then we get to our first tool that we'll use in the presentation, which is good old Turbine. Raise your hand. Who here has worked with Turbine before? Okay, so if you haven't worked with Turbine, what Turbine does is it runs a flow on another coroutine for you, and then provides methods like await item to wait for the next item in the flow. So it's just a way of testing, validating flows. So inside of our test block, we'll say await item to the wait for the next item in that flow, assert that that's our loading, await for the next one, assert that it is in fact done, which is what we expect it to be. And then we will look at the fake navigator next screen and assert that that is indeed the payment screen, what we expect for a successful interaction. And finally, our flow is going to complete. So to make Turbine happy, we need to make sure to wait for that complete event, so this flow is done, and now we have a complete test that validates everything about our flow. So we go, we run it, it passes. Great. You don't see that? Yeah, I can see this. So that's our basic test. First topic, input races. So what can go wrong in our test code that we wrote here? So I'm going to modify our code under test and introduce a simple, obvious bug. This is just, I don't know if this would happen in prod, but we're just going to take that done event and we're going to emit it before we ever read from the biometrics store. And we're going to run our test again. What happens? It passes. So this is incorrect. This is not right. Why is this happening? Well, what we'd like to do is we'd like to enhance our test a bit to detect this condition, right? We just didn't cover this in our original test. So one way that you might think of doing this would be like, well, we could await for the next item and assert that it's done. The problem with that is that this may not work correctly if we fix the test, right? There may not be a done event here at this time. We want to assert that there's nothing here, right? So we can't actually make this pass if we fix the test. What we can do instead is we can add this expect no events call. This says that we haven't received anything at this point. Now the problem is that this does fail, right? But it is unfortunately suspect. And the reason is that while it fails for our broken test, if we substitute back in our original biometrics presenter, which we know works, is good, it still fails. Why is that? If we look at our original code, see that biometrics store.read call? If I dive into this line, I will find that under the hood, it is not suspending at all. So while it is marked as suspend fund, it has the opportunity to suspend our code and kick it out to a dispatcher. It's not actually doing that. So when we call expect no events here, what we actually have is a race condition. That means that the code under test is racing ahead and and we want it to slow down so that we can detect that we've expected no events. So this is, it's not good. This is, sorry. I don't know, y'all, sometimes I get panic attacks when I have a race condition. It's just, let's talk about race conditions real quickly before I move on here. Race conditions are a serious problem. Raise your hand if you ever run into a race condition professionally. How did your day go when you ran into that race condition? Was it a fun day? No. The important thing that I want to touch on just briefly is that when we're working with coroutines, there are two different kinds of race conditions that can ruin your day to varying degrees. The first kind is what I call a real race condition. A real race condition involves threads usually. It produces potentially different results each time you run it. Maybe it gives you different results on CI than it does locally. And these are absolutely deadly in tests. I'll talk more about it later on in the presentation, but for now just know these are poison you don't want in your code base. The other kind of race condition that we run into in coroutines are what I call conceptual race conditions. The difference here is that there aren't any threads in these race conditions, just coroutines. You can't easily predict what the code is going to do without running it, but you do know it's going to run this exact same way every time that you run it. We can minimize these kinds of race conditions, but if we're writing coroutines code, we can't eliminate them. There are some things that are inherently racy in coroutines. For example, the combine latest operator, it runs everything it's combining on its own coroutine. Those are on their own threads, and they're going to interleave in ways that are unpredictable. But that's generally okay in test cases. And that's because all we need is for our test to do the same thing every time. Logically, we know it's doing the right thing. Even if in production, that combined latest may do different things at different points. It's fine. So to recap, real races require multi-threading or another kind of component that can change how your coroutines run when you run them, when your test code runs when you run it. Usually that's thread, it could be something else. And you got conceptual races, which happen when running without multi-threading, like when you run in tests or run blocking or any other kind of single-threaded dispatcher. So these conceptual races are what we have right here, and we're generally okay with them. However, we would like to minimize them. And the reason we want to minimize them is that these conceptual races hamper our ability to write a test that does exactly what we expect it to do the first time we run it. We have to run it to figure out what's going to do. So let's go back to our code here. What we need here to address our race condition is we need more control of the code under test. So what we're going to do is we're going to modify our fake biometrics. The simplest way to do this, using the tools in the standards coroutines toolbox, is to just use a channel. So a channel is like a blocking queue or something like that, but it's a lot more lightweight and it's coroutines. So by driving this with a channel, we can block that read until we send a value to our channel in our test code. By doing that, we can control the rate at which our subject under test is running. A natural question to ask is this kind of thing expensive? If you're doing this kind of thing with threading-based tools, like I've written this kind of code with array blocking queue instead of channel, that's quite expensive. With coroutines, it's not expensive because you're hitting the dispatcher, and the dispatcher is, in our case, a single-threaded construct. It just pops right up and runs the next thing. So this runs pretty quickly. Maybe it can take a while if you've got a multi-threaded dispatcher or something like that. Usually, that's not going to be the case. Now, what we're going to do instead of using a channel here is we're going to use a brand new tool that just dropped this week, which is a standalone turbine. So this is something new that we are doing called channel-based turbines. So what this turbine is just a thin, stateless wrapper over a channel. It's really just a channel under the hood but we provide an API that makes sense for testing. So based on this channel-based testing approach that we've been using for like a year inside of Cash App, like I said, it's a thin stateless wrapper. The API provides is exactly like the turbine API. So everything I showed you inside of that turbine block, you get on that standalone turbine too. You can, if you are too lazy to add a Gradle dependency, you can just use bare channels. It's fine, it does work. The advantage to using turbine over something like channels is that you get that testing-focused API, and you get, we also provide some support for non-coroutines test code. We use this so that when we write fakes, we can use them in our RX Java code and in our coroutines code. This will be introduced in Turbine 0.9, which dropped like an hour ago. So we've modified our fakes to work with Turbine. And now we add this line where we add to read results right here. So at the time that we call expect no events, we know that that read result can't have been read. So now we've got a test that will fail when they try and admit that done too early. But if they try to embed it after they do the read, it will succeed because this allows us to slow it down. It's like an interactive test. When I call readResults.add, it wakes up my biometrics presenter and then that code proceeds. Now we still have some suspect code that I'm going to call out here, but on to our next topic, which is output races. And to address output races, I want to get a little bit fancy. It's time to pull out some molecules of code. Raise your hand if you have heard of molecule, if you're familiar with molecule. Okay. Raise your hand if you have heard of Jetpack Compose. They're getting the word out about Jetpack Compose. I'm glad to see that. It's not an obscure tool. I'm joking. I love Jetpack Compose. I can't shut up about it. So, Molecule, for those who aren't familiar with it, it's basically an adapter tool that allows us to take Jetpack Compose business logic, in other words, stuff that doesn't make a user interface, and convert it into a flow. This allows us to do cool things like run that business logic in the same place that we ran RX Java business logic in production, or we can use Molecule to run our business logic under unit tests. And that's what I'm going to demonstrate here. So this is a lot of code, but what this does is it rewrites the biometrics presenter I just showed you in Jetpack Compose. So up top you see our biometrics result that is initially going to be null because we don't have a result. And then we have a launched effect in which we read from that biometrics store and then stash it in the result. And then when that biometrics result is not null, it's going to trigger a second launched effect that then performs the navigation. And then at the bottom, we produce whether we are done or loading by just looking at the biometrics result. If it's null, we know that we haven't finished processing it. If it's non-null, then we're done, and we can hit that. Our test code looks very similar. I've got this test molecule presenter call, which I'll show you. There's a GitHub repo with this code in it that I'll link you to at the end of the presentation. But it basically uses molecule under the hood to run this test, and this test looks almost identical to the one that we had before, except for this next screen call. I've swapped these so that I'm doing next screen before I validate done. And the reason I did that is that molecule throws a bit of a monkey wrench into things because the way its coroutines run, the way it dispatches things, is a little less prompt than our simple example earlier. So if we run this, even though this test looks fine, it's going to fail. So this is a problem with our test. And the reason is that next screen call. That next screen call, it happens because what's happening when we run our test is first, that initial launched effect is going to run. Third, our second launch effect is going to run. And what happens second in between the two? Your test code runs. So this is something where our dispatcher, the way it is dispatching our coroutines code, is causing, again, another race condition. So we're back in this horror land of race conditions again. So there are a few different ways of fixing it. The first one that may be tempting to reach to, like if you're debugging this and you identify that you're in this scenario, you may be tempted to do something like this. If you call run current here, that's like kicking the coroutine dispatcher, right? And like, if you have anything you haven't run, well, I'm not seeing what I want to see yet, so just go ahead and run everything, right? That totally works. That will get this test to pass. The problem is that you still have this conceptual race here. I don't know whether to add that run current line until I run the test, right? I would have to be a pretty strong coroutines wizard to know off the top of my head, oh, I better add this line. So it's not a viable way to write tests that you really have confidence in and that aren't going to grow. What we do instead is we take that next screen, and again, we replace it with a turbine. So it's doing the same thing we did earlier, except where that earlier code was an input to our test, this is connecting an output from our test. So you can make this hookup whether the function you are plugging it into is a suspend fun or not. You can call add without having any coroutine stuff or anything. So then in here, we call a wait item and our test passes. We are all good. But we still have more suspect code to talk about. Before I talk about this expect no events, though, I want to do a quick overview of input and output races. So, the two problems that you can have with input-output races are shared memory inputs and shared memory outputs. Shared memory inputs look like that big biometric store. They generally have some sort of map or var that you write into from our test code and you read from the code under test. Shared memory outputs are the opposite. You're writing something from the test scenario or from the code under test and you're reading it from the test. The downside of a shared memory input issue is that your code is less powerful. The downside of a shared memory output issue is that it's conceptually racy. So the first category of problem is, strictly speaking, not as bad as the second part. So the way I address shared memory inputs in our code base is I tend to fix these when they're in the way, or I recommend that if somebody's having a hard time testing a particular case, switch to a turbine on the input. For shared memory outputs, however, I tend to be more proactive about addressing these. So I will go through and like audit our fakes and just migrate them all en masse over to turbines or our internal tool that we used before that. Now, a natural question to ask is like, well, what if I use mocks and not fakes? I don't have an answer for you. I mean, well, the answer that I do have for you is that you can wire this up for yourself. Using a mocking framework, you can instantiate a turbine and use the mocking framework to hook up that turbine for you. But as of my last scan of all this, all the mocking frameworks that I've looked at don't have built-in support for this kind of stuff. So you're on your own, you're going to have to do it. And why use fakes instead of mocks? I, again, am partial to fakes. It's kind of beyond the scope of this talk, unless I need to kill some time at the end. So. Next, the problem with expect no events. Where if you don't expect anything, you're bound to be disappointed. So let's once again create a broken presenter that creates a problem for us. So I've modified this this composable presenter to have this launched effect that immediately sets completed to true. So it's doing the exact same thing we had before, where we moved from loading immediately to done, right? It's just done in a composey kind of way. So we pull up our test and we try and run it, and It passes. This is bad. It should not pass. It is broken. So what's the problem? Here's my worst news of the presentation. Nothing happened is always conceptually racy. And the reason for that is what you're trying to validate is that I had some interaction with the code under test and that nothing happened in response to that. Well, if the code under test is pathological, you can always write something that breaks a test that is trying to assert that, right? So like if we're talking from a strict logical perspective, like we can't validate this thing, but we want to validate it. This is a common thing to want. So this does unfortunately kind of require that we use something like run current or yield or something like that to, again, take that coroutine dispatcher and see if something happens in response to our event. Even then, it's not going to be a perfect, flawless solution, but it'll probably be good enough for our work. So we add our run current and a little comment with a frowny face, because I hate run current. We do get a failing test, so that's okay. All right. Real races. So let's modify our code one more time here. So let's say, one thing about biometrics, if you ever worked with biometrics, that token that you get, that you store, you usually have to validate with the server, because that's usually who you're trying to validate with. So we're going to add something to our app service that lets us validate that token. It returns a Boolean true that was successfully validated, and then we'll create another thing with turbines and inputs and outputs. And then, how about we say for this scenario that it's going to be one of these cases where we want to make sure that this runs even after our presenter is torn down. The pattern that you see that used for this is to launch our work into an external coroutine scope. So I've constructed a coroutine scope here with dispatcher's default as the dispatcher, and I've launched into it here. And this is the most suspect line of code in the entire talk. I'm going to talk about multiple reasons why this is problematic. But I want to start by talking about dispatcher's default. Dispatcher's default is not your friend if you are testing. Why is that? Well, let's go back in the presentation. Remember when we talked about there being two kinds of race conditions in coroutines, and that some of them are real race conditions, some of them are conceptual race conditions, and how much worse the real race conditions were than our conceptual race conditions. Well, we've got gun test. It creates conceptual races. We're stuck with a certain amount of those. If we add dispatchers.default or dispatchers.io or any other dispatcher that has multi-threaded implementation of it, we convert those conceptual races to real races. If we have real races in our code, then we're going to have flaky tests. And if we have flaky tests, we're going to have ineffective engineers who come and hassle you about why your test is failing on CI. You're not there, you're on vacation. They just ignore your test, or they delete it, or just blame the code anyway. Flaky tests are really bad. I wish I had linked to, Jesse Wilson has a great post. If you check Public Objects blog, he has an excellent post on why flaky tests are a big problem. Go read it, but that's the short story there. So, dispatcher's default is not your friend. What are we going to do about it? Well, usually we want to inject our dispatcher. So one common solution for this is to do what you would, off the top of your head think to do, which is to inject coroutine dispatcher. I actually recommend that you don't do this. I recommend that you instead inject coroutine context. The reason I recommend coroutine context over coroutine dispatcher is that this is more flexible. You can do things like add a coroutine name if you want, but my favorite reason that you want to use it is it lets you inject my favorite context, which is the empty coroutine context. Empty coroutine context is really cool because it's like the whatever context. If you inject empty coroutine context and call with context on that, It just doesn't do anything. It leaves you with the same context that you have. So it lets you inject this kind of no-op context, which I really like for testing, because if I'm passing that dispatcher down the stack, it means it'll just honor what existing dispatcher I had. So we do what I just recommended. We inject a background context with, let's say, a coroutine context, but frowny face, our code is still unfortunately problematic. The reason for that is if we inject empty coroutine context here, guess what dispatcher coroutine scope ends up using? I'm going to wait for somebody to say the answer. Default. I heard a couple different people say default, but you are absolutely right. It will run on dispatcher's default anyway. And you won't be able to see it in the code because you could be scanning the code and you're like, oh, they injected their dispatcher. We're all good. And then you have races on continuous integration. You're like, what went wrong? Well, this is what happened. This is the problem with dispatcher's default, is that because of structure concurrency, which we'll talk about in a second, because of structure concurrency, it is kind of nice to make it so that the component you're calling knows how to handle its thread best. But that means that you have situations like the SQL and the like coroutines extensions. They have a default argument that's dispatcher's default. So like you may not see that, but it's happening. Rx single, Rx completable, Rx observable, all of these default to using dispatcher's default. You're not going to run into these in coroutine steps because you're probably using these to adapt in Rx Java code if you're using them, but they're really going to ruin your day in Rx Java code, let me tell you that. There are probably more out there. The reason I know about these is that we use these in Cache App. If you use other libraries or internal tools, it's possible you're going to run into other cases where tools are silently using dispatcher's default. Unfortunately, you do have to lint against them or provide alternatives or something like that. You have to police these pretty heavily in your code base, especially if you have a large team. Now finally, let's talk about structure concurrency. Structure concurrency is your friend, and it's going to provide our answer to this constructing our coroutine scope problem. So what I recommend doing instead of doing this, we can abandon this. And the reason is that the coroutine scope constructor is inherently not structure concurrent. What I mean by that is that structure concurrent code is code where the life cycle of your concurrent jobs is governed by something you can visually see on the paper. So like if you've got code, you've got a block of code, like inside of run test, for example, that's going to bound your running code. That's not the case for constructing a coroutine scope, because when you construct a coroutine scope, any coroutines you launch into that are governed by the lifetime of this object. So as long as you hold on to that, those coroutines are alive and you have to cancel it. So you can pass around this object. I mean, this is more familiar API. This is a lot like what we dealt with before, like composite disposable, if you've ever dealt with composite disposable. So it is familiar, tempting to use, but we don't like it. We try to avoid using it. So what we do instead is we inject our coroutine scope. And you'll note that when we inject it, we take some pains to avoid introducing that as a property. We just do it as a simple parameter. That's why we have this init call that launches a job. The reason we do that is it makes it so that in our calling code, by injecting our coroutine scope and passing it down the stack, we get this structure concurrent guarantee of this concurrency. What you see is what you get. Anything inside of run test is going to stop running by the time the run test block closes. That's what structure concurrency means. So you don't have any dangling jobs. It's not going to happen. And then the other reason that we like doing things this way is that not assigning two things to a property means that jobs can be launched into the scope at this call site where I am visibly passing the coroutine scope down the call stack. But here in presenter.present or other places where code is running from my presenter, I know that it is not going to be launching any new jobs. So it strictly limits what I have to worry about when I'm managing jobs in my coroutines code. So that's all the major topics I wanted to cover. But I still happen at this point to talk about why I called the talk a few tools. It's kind of been implicit so far. Why did I do that? Here are the tools that we use that are testing specific, that are required to write great coroutines tests. There are any. Not one. Everything is gravy. To build out our initial core of coroutines tests at Cash App, here are the tools we use. We use channel, with timeout, run blocking, and turbine. We really could have done without turbine too, if we had wanted to. Turbine doesn't have a whole lot. This is the turkey of your testing Thanksgiving dinner right here. You probably do want to add run tests to that because that gives you virtual time, which is handy. This is your gravy for your testing. This makes your testing easier, nicer, it provides better APIs. But the core of what is going to make your testing great is learning how to use channels, timeouts, run blocking, injecting coroutine scopes. All of this structured concurrent stuff is what makes testing practical. And the core idea that drives that for me is the idea that my test code shouldn't be special. It should just be code. If I have my test code just be code, then when I'm writing my test code, my brain is in the same mode that when I'm writing my prod code. So if I solve a problem in test, and it can translate across to my prod code, I can just move it over. If I have something that I need to do in prod that I need to validate a test, I can just move that over as well. So that's kind of the big idea here. We're using the core coroutines tool set with some thin wrappers on top of it, like turbine, to make our test better, easier to write, easier to read, easier to understand. So what was in this talk? You can gain more expressive power by using channels and turbines to communicate to the code you're testing. You can reduce brittleness as well. Make sure to weed out any intentional or inadvertent usages of dispatchers that default to avoid real races and flakiness on CI. And use structured concurrency to keep tests self-contained. There is all the code that I was using to hash out all the things I wanted to say here, and I illustrated the talk. You can find it in this GitHub repo if you're interested in browsing it after the talk. And then as far as finding a turbine, if you look at that repo, you'll find that I've copied and pasted a lot of stuff in there. And that's because this stuff was just released. So Jake released this like an hour ago. So it's now out there. If you want to check out Turbine 0.9, you can see all this stuff. I will say that this is going to be continuing to evolve in the next few months as we hash out how we want to support cases like that expect no events, that kind of thing. Things that were not in this talk that I might have been able to put if I wanted to. One is testing state flow is really unlinked. I have a whole rant on this. You can find it at my blog. Short story is if you can avoid testing state flow and test regular flow, do it. Fakes are better than mocking frameworks. I did write everything I had to say about this in one slide. Right after the thank you QA slide if you want to see it. And come to work with Cash App. It's great. All right, things that were not in this talk that I just don't have much experience with. One is Android X view models. We don't use them at Cash App. We use the API I showed you. The view model scope call in particular is problematic. It's because it's not structured concurrent. It does construct a coroutine scope under the hood. It does require testers to assign a coroutine dispatcher by hand. So these are solvable problems, but not ones that I dealt with or that I identified any solutions for. Mocking frameworks, as I said, I don't have any guidance on that. Non-structured concurrent code. Non-structured concurrent code is necessary. It's not my main jam though, and I don't generally unit test this code when I do it. The reason is that I write this code when I'm in a view or something like that I'm not going to be writing a unit test for. I will probably write like a paparazzi test or something like that for that, but not this kind of stuff that I showed in this talk. And that's it. Thank you so much. Our community is awesome, and I'm really grateful to be speaking again at a conference again. This is my first conference since the pandemic. It's awesome. Thank you all for being here. I'm very grateful. And that's it. Does anybody have any questions?
Thank you very much. This is very helpful. So recently we updated our text because of Kotlin Kotlin text upgrade from 1.4 to 1.6.
Yeah, did you run test versus run blocking test?
And we used confined dispatcher, and we get rid of run blocking. Instead, we're using that one. I'm not quite sure about this. Basically, it means it's not guaranteed which context uses I'm running in the working, but it's try to, they say, try to make the high-level side to be put the test in high priority. In other words, we don't have to run concurrent. What do you think that? What's the problem about that?
This is one of the reasons why I included the molecule example here, is that there is this phenomenon where in the testing tools, they're trying to add tools that make it so you can just write tests and not worry about this stuff. I think that they're probably going to continue to try and make this stuff better. I make it my habit not to rely on that. I prefer to write my tests such that I don't need those tools to do my thinking for me. I want to write my code so that even if I ran it without any of this testing stuff, it works. And the reason is that I don't want to put myself in the mental habit of writing code that doesn't work the way that coroutines code works. Like if I write good coroutines code that I can predict what it does, then I can write good tests. That's my personal approach. So I can't speak in any great detail about unconfined test dispatcher. I can say that I don't think it's particularly problematic. But I try to avoid situations where I solve a problem by using one dispatcher over the other. Any questions?
Question. I noticed one of the things you wrote, one of the three things was with timeout.
Yes.
Are you talking about, you're not talking about, let's click, test and click event, because there's some time.
No.
Okay.
Yeah. You want me to just go ahead and dive into why I wrote it?
Dive in.
Yeah. So let's go back to some test code. Where is our test code? No. All right. So here's why we continue to lean on with timeout. I'm actually getting into it with Jake on the turbine repo about this right now. The reason I continue to advocate for leaning on with timeout is because we see in practice in real world tests that hangs are a common failure mode that indicate real business logic problems. So a common example would be like, say somebody came through to refactor things and forgot to event the done event, right? That kind of thing happens all the time. This is a simplistic example, but we see it in practice that happens all the time. So what with timeout lets us do is fail those tests fast. So when I do a wait item in here, underneath the hood, I have like a with timeout 1,000 seconds, and that allows me to, one, fail the test relatively quickly, and then I need to be quite up here for the streaming, sorry. One, it allows me to fail the test relatively quickly, and then two, it allows me to see in my stack trace that it failed on this line specifically. Okay, yeah.
So when you talk about my molecule and how I kind of reflect places that are floating or walking, when you're doing your navigation, like if some certain condition is, you're navigating to the screen, you did that within the launched effect.
Oh yeah. Let's that was let's find that code. That was in here, right?
Yeah. So I was wondering, like, if your navigation is kind of like being run as a side effect, how would you write a test to make sure that your navigator was actually called?
Well, that's what we're doing here, right? The way we do it is with that await technique. So we try not to rely on the specifics of when that launch effect is invoked.
Okay.
But if we write our test and say, await for the next screen to be emitted to be this, then it will let any coroutines or anything else do their business until that happens. So that's what we're dealing with this. So we have. All right, I think I am. I think I'm past time. All right. Okay. Well, thank you so much for being a wonderful audience, and again, thank you so much for the opportunity to present. Thank you so much.